Hello everyone! Welcome to today's presentation on the concept behind the design of steel beam. My name is Eli and I'm excited to guide you through this topic. First of all, just a quick background. Beams are the horizontal structural members that support transverse loads, making them subjected to flexure or bending, where the commonly used cross-sectional shapes are W, S, and M shapes. In steel beam design, the common design methods used are the ASD and LRFP. ASD stands for Allowable Stress Design, in which it limits stress to a fraction of yield strength, using this formula of applied moment is greater or equal to nominal moment over 1.6 equals to 0.6. While the LRFP is the load resistant factor design, that is the factor's load and resistance to ensure safety under conditions with a formula of maximum moment is greater or equal to the resistant factor multiplied by the nominal strength. The beam undergoes stages of loading, wherein at first it's in its inelastic stage and then the yielding begins to occur. As loading continues, yielding spreads into the web of the steel beam until the entire cross-section has yielded. Once the entire cross-section is yielded, any further increase in the load will cause the collapse of the beam. This is because all members have reached the yield plateau of stress-strain curve, or basically, the yield strength and unrestricted plastic flow will occur. With that, a plastic hinge is formed at the center of the beam, and it constitutes an unstable mechanism. That plastic moment capacity is the moment required to form the plastic hinge. Now you might be wondering, what exactly is a plastic moment? Why is it important, and where do we apply it? Well, let's dive in. At its core, a plastic moment refers to the maximum moment that a material can withstand before it undergoes plastic deformation. In simpler terms, it's the point at which a material, like steel, begins to bend and change shape permanently under stress. This concept is crucial in engineering and construction because it helps us understand how structures behave under loads. By knowing the plastic moment, engineers can design safer and more efficient buildings, bridges, and other structures. Let's talk about why we need to understand plastic moments. Imagine designing a bridge that must support heavy traffic every day. If we don't account for the plastic moment of the materials used, we risk structural failure. Understanding this concept allows us to first ensure safety. By predicting how materials will behave under stress, we can prevent accidents. Second, optimize design. Engineers can use materials more effectively, saving costs while maintaining safety. Third, to innovate. Knowledge of plastic behavior opens doors for new materials and designs that can withstand extreme conditions. So where do we apply this concept? Actually, the applications are vast. A brief example of these are buildings. In skyscrapers, understanding plastic moments help ensure that they can withstand wind loads and earthquakes. There is also bridges, where engineers use this concept when designing bridges to ensure that they can handle heavy vehicles without collapsing. The plastic moment is not just an abstract idea. It's a fundamental principle that plays a crucial role in engineering and design. By understanding how materials behave under stress, we can create safer and more efficient structures that stand the test of time.
So for the first problem, we are asked to determine the elastic section modulus, which is S sub x, and the yield moment, which is My. We are also asked to look for the plastic section modulus, which is Z sub x, and plastic moment MP. We have a given of an allowable bending stress of 345 megapascals with a steel A572 grade 50. So to start solving, we have these formulas to remember to guide us in our solving journey. We also have a table to help us solve things easier and faster. So first we have to divide our beam into three different areas, three different components, which is the upper flange, and we have the second area, which is the web, and then the third area, the lower flange. So for our first column, we have a formula of I equals to base times height cubed over 12. The upper flange has a base of 203 millimeters with a height of 225.4 millimeters. So cube over 12 will result in an answer of this. It's Since the upper flange and the lower flange are symmetrical, they will have the same exact value. The web has a base of 12.7 multiplied by 25.4.2 millimeters. Cube over 12 with an answer of this. We have the second column, which is A equals base times height. Once again, we will get the areas of each component. The upper flange with a base of 203 multiplied by 25.4 with an answer of this, similar to the lower flange. And our web has 12.7 millimeters multiplied by 25.4.2 millimeters with an answer of this. Now, we are being asked for the distance of each component's centroid area over the neutral axis. So, half of 25.4 plus half of 254.2 millimeters is going to result in this answer, similar to the lower flange. And since our web has a centroid area right by the neutral axis, it's going to have an answer of 0. We can now solve for the moment of inertia, which is I plus area distance squared. And with an answer of all of these, get the summation in order to have the final answer. So now we can finally get the elastic section modulus by taking the moment of inertia, dividing it to C. C is the distance of the top of the beam towards the neutral axis, so half of 305 millimeters is going to result in 152.5. Divide the moment of inertia to that distance, and we will finally get the elastic section modulus. Now we can take our elastic section modulus and the grade of our beam, which is 345 megapascals, multiply them, and we will get, and what we will have is the final answer for the yield moment. So for the second part of our solving, to find the plastic sectional modulus and the plastic moment. The first thing that we should do is we should cut our beam in half. We once again have a table to help us solve things easier and faster. Our component, the upper flange, and the second component, which is the web. So the first thing that we need to do is we need to once again find the area. With a base of 203 and a height of 25.4, we once again have this answer, and a web with a base of 12.7 multiplied by, since it is cut in half, we have a value of 127.1 with an answer of this. Now get the summation of both areas and we get this answer. Now we need the distance from the centroid areas to, once again, the neutral axis. This time is the plastic neutral axis. So half of 25.4 millimeters up until the plastic neutral axis, which is 139.8. Same thing with the web, which is 63.55. Now multiply both the distance and the area, and we will get these answers, and once again, get the summation. After getting the summation of the product, we now have this formula. To get the y bar, we need these values, which is area 1, y1, area 2, and y2. Area 1 being the area for the first flange, the upper flange, and area 2, the area for the web. And then we have this distance for the y1 and the second distance for the web for the y2. After getting each of their values, substitute the formula and we will get this answer. To finally get the plastic section modulus, we just need to accomplish the formula, the total area divided by 2 multiplied by A. And A is solved by 2 multiplied by y bar. So that will be 121.62 multiplied by 2, which is 245.24. Now substitute these values to the formula and we will get the final answer of the plastic section modulus. So now we can finally get the plastic moment by multiplying Fy to S sub x. Fy being the allowable bending stress, so 345 multiplied by the Zx, which is the plastic section modulus. And you will get the final answer of the plastic moment being 568.212 kilonewton per meter.